Okay, so in this section we're going to take a little bit of time and we're going to talk about drawing inferences for a slope. Okay, so what's going on here is you have a set of data that has two characteristics. It has an x, an explanatory variable, a y, a response variable. And what we have is we don't have all of the points in the population. We just have a subset of points in that population. Okay, so here's my subset of points. And looks like I might have like positive correlation here. So I'm going to assume that there's going to be like some sort of line of best fit. And we're going to say that this line of best fit is y hat is equal to b sub 0 plus b sub 1 times x, right? So this is a point estimate for the regression line that would be the regression line if I had all of the data points, right? So the regression line with all the data points is, a little bit more significant, right? It's like kind of so it's going to say that mu, right? So we'll just use mu, right? The mean regression line is going to be some beta 0 plus beta 1 times x. Now, what we're most concerned about here is not actually the intercept, but rather the rate of change. How well does this b1 represent the actual rate of change in the this should be mu sub y. The actual rate of change in the population, right? The mean rate of change in the population. So, a couple of things that's going on here, right? So, we know this. We know that the mu for b1, right? So the mean value. We want to know how b1 is distributed. Beta 1 is. Sorry, the b1s are distributed, right? So, oops, sorry, Control Z. There we go. We want to know how the b1s are distributed. So they're actually going to be distributed normally with a mean around the actual slope b1 with a standard deviation, and this is going to be weird. It's going to be like sigma over the sigma of the x's times the square root of n. Okay, so the weird thing in this is that this sigma up top, the sigma up top is the standard deviation of the residuals. So if you make a list of the residuals and you find their standard deviation, that's going to be this. This is the standard deviation of the x values. This is the number of points in the sample. So if we have the right conditions, b1 is distributed centered at beta 1 with the standard deviation of sigma, which is the standard deviation of the residuals, over the standard deviation of the x's times the square root of n. All right, so what do I need to make this work? In order to make this standard deviation work, I have to have n has to be less than 10% of the population. So that 10% rule is still going to give me the standard deviation. How do I get normality? Well, if the sampling distributions are going to be approximately normal if the values of the response variables, so the y responses, right, follow a normal distribution for each value of the x. Okay, so this is kind of a little bit tricky to see, but the way that you would normally handle this is you would look for a residual plot, and if the residual plot has more dots closer to the line right, and fewer dots further away for each value of x, then we can assume normalcy. So unless you see something that directly contradicts that in the residual plot, we're going to go with normalcy, because in most circumstances that they are, there are some circumstances where like you'll see, like in the residual plot, it's very clear that like the residuals are all far away from the line, or they're all like equally distant from the line. They're not like bunched up in the middle and then thinning out as you get further away. So basically, to make an inference, you have to actually meet 5 conditions. You have to have a linearity condition, so it has to look like the data has some sort of what do you call it? Some overall linear pattern. Usually you could see that just directly in the scatter plot. There has to be a sense of independence. So like the idea here is that the x, changing the x, like the relationship between two x's should not give you the relationship between two y's. That we'll take a look at this. Normally, if so long as you're not like sampling with replacement from a small set, there are some other like if you're looking at the details of the problem and it looks like, hey, these dots aren't independent, then you have to call that out. So that's got to be there. Normalcy. So this is what we just talked about. That the residuals have to be normal. So the residuals have to appear to be normal for each x value. And that you can get by looking at the residual plot. So as you're getting closer to 0, they should be more bunched up. Further from 0, they should be further apart. You have a condition of equal standard deviation per x value. So you shouldn't have it like at one x value, everything's really close to 0 in the residual plot. And then like later x values, everything's really far away. So you should have a sense that like the distance from 0, the spread of things from 0 at each x value should be relatively consistent. And of course, we have the random condition, right? So we would like to say that these dots are somehow a random sample from the population. So a lot of this doesn't make a whole lot of sense until you like try to put it into motion. And because a lot of this you're going to do by using the calculator, that's how we're going to kind of proceed from here. Okay, so we've got a little bit of a 2-variable data set here where you have miles driven, that's like how many miles are on the car, and then the sales price of the car, right? So there should be like a negative correlation here. I would think that the further you drive the car on average, the less the car is going to be worth. So we're going to punch these numbers into the calculator and kind of see what's going on here. Okay, so I've gone ahead and I've put all the data in the calculator. So we got to kind of look around and see if this is going to make sense for my testing here. So I'm going to clear out everything that's in my y equals. And I'm just going to look at the scatter plot at first. Okay, so let me go to the plot 1. So let's go make a scatter plot there. Turn the plot on, scatter plot L1, L2. Let's use the little crosses. And then we'll go zoom 9, and there's a scatter plot. So on the linearity front, it is pretty reasonable to assume that that is like a what do you call it? Negative, linear. It seems like it's a linear data set that has a negative correlation to some extent. There's no reason for me to think that these cars are not independent of one another in any way, shape, or form. So I think we've got linearity. I think we have independence. In order to get to normalcy, we have random as well. Like we're going to assume that these cars were selected at random from the population. So the last two is the idea of normalcy and the equal standard deviation. So to get to normalcy, I want to create a residual plot. So in order to do that, I want to run the linear regression. So I'm going to go calc, look down to number 8 here. I'm going to use L1 and L2. We'll store the regression equation in y vars y1, and we'll go ahead and we'll calculate that. So yeah, it's got a pretty solid negative correlation. The slope that it's giving me is this like 16 cents per mile driven, right? So it seems like the cars on average are dropping 16 cents per mile driven. Now I stored that in Y1, so I should be able to kind of graph the stat. There's the linear regression in the scatter plot, right? But now what I want is a residual plot here, right? So if I think about this, my residuals, I believe, so let's go back to the main list here. I should be able to make the residual plot by going here. L1 I'm going to keep the same, and then I'm going to go to, I think it's second stat. Yeah, it gives me number 7 is, oops, not that one. Let's try that again. Second stat, number 7 is the residuals, right? So in y equals, I want to clear that out because I don't want that as my my line, right? So because I actually want the x-axis as the line for the residual plot. So I go zoom 9, and there's my residual plot. All right, so let's think about this. I have no reason to think that these are not normally distributed. I mean, it seems like most of the data is kind of bunched up around the line. I don't have any reason to think like there's like no like band of data that's like further away from the residual or anything like that. And it seems like the maximum distances from the lines are about the same for all the x values. So I'm pretty confident that I can make the inferences that I need here, that I have met all 5 conditions. All right, or at least I have no evidence to say that I can't. So the first type of inference that I want to make is a confidence interval for the slope. So the way I can do this is I can go to stat, test, and way down at the bottom here is a linreg t interval. And that's the one I want. So I'm going to do that for list 1 and list 2 with 95% confidence. And I'm going to store that regression equation back in, what do I want, vars, y vars, y1. So that if I graph it, I get it. And I'm going to calculate, right? So where I'm getting here is my my confidence interval, right? So I'm 95% confidence. So like the point estimate for the slope is negative 0.16. So that means I'm losing 16 cents for every mile driven on average. So the actual amount that I'm losing per mile driven on average is somewhere between 22 cents and 9 cents per mile, maybe 23 and 10 cents per mile. And the other data that I'm used to down below here is there. So y degrees of freedom 14. That means that in my data set, if I go and I look, the data set itself should have 16 points of data. Yeah, see there's 16 there. I have to take away 2 degrees of freedom, 1 because of the x dimension, 1 because of the y dimension. Okay, so if I go back and I put that stat plot back in, make it the scatter plot instead of this. All right, so zoom 9. There's my data with that nice thing. But I also now know the confidence interval for 95. Oops, that's not what I wanted. The confidence interval for the slope with 95%. I now know that that slope is somewhere between 23 and 10 cents per mile driven, right? So that's kind of interesting. Now, that should be statistically significant. So what I can do is I could check for statistical significance here. So if the slope is 0, then there is no correlation in the data, okay? So there's a point here where like slope of 0 means that my data is not likely correlated. Because hot mass is going to give me a residual or a regression line with a slope of 0. So what I'm going to do here is I'm actually going to test against 0. Now, because my assumption is that my data is negatively correlated, I'm going to do my test in the following way. I'm going to say my H null is going to be that the population slope is 0, and my HA is going to be that my population slope is less than 0, right? Because I believe this should be negatively correlated. So I'm claiming that it's negatively correlated. If I end up supporting the alternate hypothesis, then the data supports my conclusion. If versus there being no correlation, right? So we'll kind of fix an alpha at 0.05 here and conduct this test. So what I need here is I go stat tests, and I'm going to go linear regression t-test. Okay, so my data is coming from L1 and L2 with a frequency of 1, and saying beta or rho, and I want to have it as less than 0, because that's my alternate hypothesis. Now, the reason why beta or rho can both be considered as 0, because rho is the population correlation, beta is the population slope. If I have a population slope of 0, my correlation is also going to be 0. So that kind of works out nicely. I calculate, and I get my infamous p-value here, right? My p-value is very, very tiny here. It's like 6 times 10 to the negative 5th, right? So p-value is 6 times 10 to the negative 5th. So p is significantly less than alpha. So p being less than alpha says reject the H null, which means that my data supports my alternate hypothesis, right? That the actual population slope is negative. So I can now assert that I have negative correlation, or at least the data supports the idea that there is negative correlation between the miles driven of a car and its sales price. Okay, so this is how I would do significance testing in this space. Alright, so we're going to play around with this for a couple days. Hopefully this kind of gets you started into thinking about it. We only play with the slope. We don't play with the intercept as a point estimate. The slope is pretty straightforward because it's normally distributed. So we're back to t-tests, and we go from there. Alright, so we'll take a look at this in class.